Okay, let's try to find the derivative of the natural log of xy plus 5x equals 30. So we're going to find dy dx implicitly. Well, natural log of xy, that means we've got a product. So I'm going to break that up into two logarithms. The natural log of x plus the natural log of y plus 5x equals 30. So rather than have to do the product rule, I can just expand. So I'm going to rewrite this by expanding it. I know it said a try, but I wanted to do that first step with you. And now what I'd like you to do is try and finish the problem and see if you can get to the answer I get to. Okay, welcome back. If you haven't left, make sure that you press pause. So 1 over x plus the derivative of natural log of y is 1 over y times the derivative of y, which is dy dx, plus the derivative of 5x with respect to x is 5, and the derivative of a constant is 0. I'm going to isolate the 1 over y dy dx on one side of the equation. So I've got negative 1 over x minus 5, and then I'm going to multiply every term by y, and I get dy dx equals negative y times 1 over x plus 5. So see how I just factored out that negative and I put it out there with the y because I multiplied both sides by y. So I multiplied by y, whoops, not a colon, there, multiply by y, and then multiply by y. And rather than just have y times the quantity, I factored out the negative so that the binomial inside was a little cleaner. And that's our answer. Okay, let's try another one. Let's see if you can do this one. I can sense that you are feeling confident. So let's try this one. The second derivative of f of x equals the log of x. F of x equals the log of x. Okay, here we go. F prime of x is equal to the derivative of log of x is 1 over the natural log of the base, which is 10, times 1 over the argument, which is 1 over x, and then times the derivative of the argument, which is just 1. So that would be f prime of x would equal 1 over x times the natural log of 10. Now the natural log of 10 is just some number, but we are going to write that number we're going to write the argument in parentheses, but we're going to write that number on the right hand side of the x just because it's, like I said, it's a little bit cleaner that way. So now we need to find the second derivative. Now the second derivative is, it's just, look at it, it's pretty cool. The second derivative, let me come over here and show you. So this, I just want to show you 1 over x times the natural log of 10 looks a lot more confusing than it is. It's 1 over the natural log of 10, which is a constant, times 1 over x. That's all it is. That's all it is. So now when we find the second derivative, that constant, this constant that's yellow, that's just going to stay there, right? And then we're going to multiply that constant, 1 over the natural log of 10, we're going to multiply that by the derivative of 1 over x. And the derivative of 1 over x is negative 1 over x squared. Now that's not even our logarithms or our exponential derivative. So that second derivative is actually old stuff, right? Definitely. So we're going to have negative 1 over x squared times the natural log of 10. That's our second derivative. And I'll box that. Excellent. Okay, let's do a word problem. Radioactive carbon isotopes have a half-life of 5,715 years. If 1 gram of the isotopes is present in an object now, what amount will be present after t years? So this we're going to go back and this is actually something you might have learned in Algebra 1, so we're going to have to go back and learn how to write that equation. So what amount will be present after t years? So that equation is your end amount. I'm using this formula right here, y equals a times b to the x. I actually just got done teaching this in Algebra 1. So a is going to be our end amount, right? That's our end value, is equal to our initial value. Okay, so our initial value is going to be 1 gram. That's your initial value. Times how much is going to be present. We're talking about a half-life. So a half-life means I'm going to retain half. I'm going to lose half, but I'm also going to retain half. And I'm going to have how many 5,715 year periods. So it'll be 2t over 5,715. So if there's one 5,715 year period, that means time will equal 5,715, and I'm going to lose half once. If we have 11,430 years, that means that's 2 half-lives. Better not write it like that, 2 half-lives, right? So it just tells you the exponent is the number of half-lives. So this is the number of half-lives. And in order to do that, you have to divide your total number of years by 5,715. So that's how much will be present after t years. 1/2 raised to the t over 5,715. Now, at what rate is the amount changing when t equals 1,000? Actually, we're going to make this t equals 10,000. Okay, we're going to make it t equals 10,000 years. And that's because that's what I have the answer for. So make sure you have t equals 10,000 years. So at what rate is the amount changing? That means I need dA dt. And that's going to equal the derivative of 1/2 raised to the t over 5,715. So I'm going to have the natural log of 1/2, natural log of the base, times the actual exponential times the derivative of the exponent, which is 1 over 5,715. And now I'm going to evaluate that when I put 10,000 in for t. And when we put 10,000 in for t, we'll have the natural log of 1/2, I'm just going to put 0.5, times 0.5 raised to the 10,000 over 5,715 power, times 1 over 5,715, and I put all of that into my calculator, and I get approximately, I'm going to give you a minute to put that in, I'm getting a negative 0.4036, so that's 36 billionths of a gram per year. Now, what's the negative mean? This negative means that the amount is changing by decreasing. So the change is decreasing. So meaning it is decreasing. And then what's it decreasing by? 0.00036 grams per year. And that's a word problem. There you go. There's an application of how we would find the rate at which an amount is changing after 10,000 years when we're dealing with an exponential function.